Thank you very much for inviting me to speak with you today about enhancing resilience by applying performance-based asset management. As mentioned, I'm John Seikmeier with the Minnesota Department of Transportation. Very happy to be here. Welcome, everybody. So I'd like to begin with some acknowledgements, and of course, with all the research and implementation that we're going to be talking about the next couple of days, it's just critical that we have partners. And we're very fortunate to have had our local governments and the DOT districts very much involved and supportive over the many years that of the things I'll be talking about today. Our contractors as well, it's impacting their projects. And so when we get out there and do pilots, they have to be very flexible. The consultants, the manufacturers of the equipment, all these people, certainly very thankful. Other DOTs, many that are on this call today, Federal Highway Administration, a lot of coordination, of course, the universities across the country, and all, very much supported by the National Academies, TRB, and CHRP. So without all these partners, we certainly wouldn't be able to share the information that we have here today. I'll follow this outline, start out with some introduction opportunities to sort of the why of why we're doing this work. I have a couple of construction implementation examples, so really what's on the ground, what we're doing, and then just real brief at the end, just a slide or two on lessons learned and next steps, really the what's next. Well, by way of introduction, I'll be speaking pretty much about recycling and reclamation with respect to roadways. So I think our next talk will be more about structures, bridges. I'll focus pretty much on roadway construction and those assets. The Minnesota DOT, we have been trying hard to implement intelligent compaction for quite a few years. And in 2014, we laid out a roadmap, and this was really critical because it let our construction industry know that we were very serious and that we were going to be requiring intelligent compaction during roadway construction on our projects on the trunk highways across Minnesota. So this, they had to start buying more equipment, and there was a timeline here that laid out what % of the projects we expected to include intelligent compaction over the next several years. And so currently we're actually at 100% of the asphalt paving projects in Minnesota require intelligent compaction. Some of the key benefits of intelligent compaction, primarily, certainly the number one is the construction optimization for the contractor. This is the contractor's equipment, it's the rollers, it's their pavers. And so, it's a huge optimization tool for them. We get, and they have then 100% coverage. So we don't just have a handful of point tests. We have 100% the actual equipment is doing the measuring. Also, we're able to link the construction measurements to the pavement design because we're using similar properties. When you're applying loads, as an example with the compaction roller, you're applying loads from the drum and measuring the response. That's not unlike when we drive a truck on the finished pavement. And so these things are the properties are much more closely matched between design and construction. And finally, soft spots. Ideally, we would be finding more areas that need compaction deeper in the foundation. And so as we go up, we build the roadway, we're fixing things as we go. So this is kind of why we're really solid on implementing intelligent compaction. The opportunities, and I'll talk about these 6 things. I got a couple slides on each. I'll be mentioning eliminating unsafe testing, addressing national priorities, enhancing roadway resilience, demonstrating innovation, improving asset management, and of course, increasing cost effectiveness. So by way of, what do I mean by this unsafe testing? Well, actually, when I first got involved with this a couple decades back, and I had been doing construction testing as an intern during school, came to the DOT, and we were doing a lot of, of course, doing density tests. And I was very familiar with these tests, and we had our construction engineer for the state of Minnesota was very interested in getting rid of, or at least providing options that would reduce the danger with the inspectors doing these tests. And we'd actually had inspectors, at least one killed and several injured, being in these, down on the ground for many minutes. So, a huge initiative was, can't we replace this unsafe testing? We in fact moved pretty fast, got that done, provided a couple options: the dynamic cone penetrometer, lightweight deflectometer. As far as addressing national priorities, all the DOTs have been actively working to address what was passed by Congress, MAP 21 in 2012, and the subsequent federal highway bills have reinforced the need for measured outcomes that are performance-based. So what I'm going to be speaking more about today are what tests, what processes can we put in place that are much more, again, performance-based, linked to design, linked to long-term performance, and that's all essentially mandated by Congress and then by the rules that Federal Highways puts in place. The Society of Civil Engineers was already mentioned. They have professional standards as well as AASHTO. So all these important professional organizations are encouraging us to move expeditiously towards these goals. As far as asset management plans, we're familiar with the rules that have been adopted then by Federal Highways that are posted in the Code of Federal Regulations. Again, asset management plans then talks about measures. So we're improving those measures. In Minnesota, we have a couple of measures. These are maps of the trunk highway system in Minnesota. The map on the left is basically the smoothness. So this is just the trunk highways. Smoothness looks pretty good. We measure the smoothness every year, every mile of trunk highway, and we're doing a pretty good job keeping things smooth. But unfortunately, the remaining service life on the right, many areas that could be better. And with the new infrastructure bill, we're hoping to do some more permanent, deeper fixes so that we end up with a more resilient smoothness. The map on the right is remaining service life, and what influences that is what's holding up the surface. And so if the foundations are not so good, then we have a very low remaining service life, and all these red sections of trunk highway have an estimated remaining service life of 0 to 3 years. So that's not good. And we hope to be able to, as we improve these foundations, as we rebuild these sections, we make this all last longer. Of course, try to avoid, we're trying to avoid what Mark Twain advised us about many decades ago. And so we'll try to follow a much more engineering oriented approach and improve these foundations. So we're not just creating a patchwork of holes. How do we do this? Here's a little bit busy, but maybe I can quickly explain how we establish that remaining service life. So on the left side here is the ride quality, and we have a scale so that high numbers are good. This is essentially the smoothness. Poor is lesser numbers. Now each year in the upper left here, we measure the pavement smoothness. That's these solid triangles in the upper left. And then into the future, we project based on past performance. That would be the open triangles based on how we built things, based on the foundation, based on the specs. That's the expected decay curve for the smoothness. Now, if we improve how we do things, we build a better foundation. The expectation is we might be able to extend the remaining service life and gain years. And so that's sort of the vision. And if we actually we look at a project, this actually is happening now. We're starting to have measurements, and this is a project we built using intelligent compaction, using lightweight deflectometers, using test rolling. Also, we kind of threw everything at this, and then we've also done real proactive maintenance over the last many years. So having built this with a smoothness typical at 2007. Now we have measurements through 2020, essentially no loss in ride. So essentially, very exceptional. This pavement's going to last quite a while. And so when you build it right, lasts a long time. And of course, besides building it right, it requires maintenance along the way. So this is we're working, making sure the surface does not fall apart using proactive maintenance treatments. The legislature in Minnesota is encouraging us to continue this work. They just passed a law this last just a few months back and earlier this year, encouraging us to continue on this process of better asset management and making it more clear that besides bridges and pavements, as are required by the federal legislation and rules, we have to include geotechnical. So this would be all the pavement foundations and other work. So between pavement and geotechnical, we're certainly covering the roadway engineering. If you're interested in learning more about geotechnical assets, many states are working on these. Here's the Minnesota DOT website, talks about what we're currently doing with geotechnical assets. Our grading and base manual mentions other assets that are included by other states, and there's an NCHRP report just produced a couple of years back, 2019, on geotechnical asset management. There's a manual and a report, so those are certainly great resources. A little bit of a history. I'm going to less than 5 minutes here on I've been talking a lot about some kind of innovative things, but if you go back and you look at with respect to some of these tests that we all have are currently doing, as at least either partially or completely. For instance, this density testing for compaction. I think many of us recall that typically these are referred to as Proctor tests. There's a laboratory test that's done. But essentially, the bottom line is that Ralph Proctor, he was an engineer building dams, big earthen dams out in California. He did not use density. His focus was on strength, and his focus was on construction. Optimum moisture is for compaction, and the desire to avoid rutting as he was trying to build. He and his technicians and the contractors were trying to build these huge earthen embankments out in California. And just a shout out to Missouri University of Science and Technology, Dr. Rogers there. These are slides, photos that he's been using in his coursework. So again, thank you, Dr. Rogers. But anyway, Proctor was building these huge earthen dams. You can see the type of all the equipment here, and he was not using density as a control measure. He was using a performance test. Unfortunately, that message was not transmitted well. People went out there, ASTM went out there and talked to Proctor, and essentially did not capture what he was doing. And we ended up with a density kind of a spec that really didn't represent what he was doing. And when we went to World War II, things went bad. We built runways, they fell apart, and the Corps of Engineers got involved, and we ended up with what we call a modified Proctor test. And that kind of got us through up to the present time. But there was a team that was put together. They looked at all these things, and essentially, if you look at these names here, a lot of very important people, highly respected in the geotech and pavement area, determined that in fact we were not following Proctor's intent. Hveem and Carmany, clarify that density is really not all that useful. Proctor, then he writes papers after the Second World War trying to clarify that we'd misinterpreted what he was actually doing, and he didn't use any of this dropping weights in the lab stuff. So anyway, the history is pretty clear that we're just returning to what Proctor intended many decades ago. Again, this was in the 30s and 40s. He was succeeding in California, and we're nearly a century later trying to get back to what he was doing then. So anyway, no reason to be held up on tradition here. So Proctor's penetrometer is on the left. The DOTs are implementing dynamic cone penetrometers in Minnesota. Many states around the country are using DCPs. We've also allow the lightweight deflectometer. Indiana is another one. You know, if you're looking for implementation of the lightweight deflectometer, the Indiana DOT has more than 100, I think, LWDs between their staff and the testing contractors in Indiana. So they're certainly a resource. So options. So as we're building roadways in Minnesota, when we're building the embankment, we provide a bunch of options for our inspection personnel. They can select between the designer and the inspectors. They can either use the lightweight deflectometer, this DCP, quality compaction, which is, if we have full-time inspection, which is very rare, then we don't do a lot of tests. We have a person there that knows the proper procedures, knows how much compaction. The testing is very, very minimal then, because we have eyes on the ground that actually can have the experience to know that things are done well. And we have test rolling, and we still have density. By way of intelligent compaction, here's a slide, just I think a great slide, very clear from our partners at the University of Texas, El Paso. Shows the roller in the middle, and then these intelligent compaction rollers, again, I mentioned they have, the operator has a screen that's in the upper left. They can see immediately how the roller is behaving with respect to the ground. That's through the measurement of the drum in the lower left. The upper right sort of points out that these rollers are either tied to satellites or to ground base stations, and that puts all these measurements on a map, lower right, both immediately to the operator and then, of course, stored long-term for quality assurance purposes. The specification is, here's the sort of the current Minnesota version, intelligent construction technology. Again, on every job, every asphalt job that is greater than 2 lane miles, so that's anything of any consequence, now requires intelligent compaction and thermal profiling. And that's the materials are listed here. That's reclamation, ultra thins, the hot mix asphalt, stone matrix asphalt, cold in place recycling, and cold central plant. So not all the foundation yet, but we're slowly but surely picking up all the foundation layers. Again, these partners around the country are doing great work. Here's, again, I mentioned the University of Texas, El Paso. Here's a recent report just from last year, tying the intelligent construction compaction measurements to the mechanical properties used in design. Great resource for those that want to learn more about this. Another huge thing is that moisture content. We all understand that the compact materials, they have to be the correct moisture, and we've been at this along with other DOTs for many decades, really. Starting with really a huge amount of work by Jill back in 1998, her thesis on seasonal properties during pavement design and how they perform over the long term. And then Ruth in the mid 2000s really got into unsaturated geomechanics, and there were a couple of NCHRP reports, an IDEA project, and then the full-blown NCHRP report that cover these things. So again, you can contact me, Google this stuff, a lot of work. Currently, moisture, we have just again with these compactors, we've got people like Dr. David White and his company in Geoset. Here's a slide from earlier this year at the TRB annual meeting, where he's mapping moisture content during construction. So again, all these technologies, a lot of these things that are out there, people are using them. It's all very doable. Why? Because we're hoping to increase cost effectiveness. Again, I've mentioned we've been at this for a couple of decades, like many of you, and better material tests. We understand that when you're going to, the whole concept of using mechanistic pavement design, mechanistic testing, all these things are going to be able to help us fine tune and enhance pavement performance and build things more effectively. All this in mind, of course, I'm a geotech pavement foundations, kind of a rock and soil guy, and I appreciate this quote very much from Richard Handy a few decades back. Virtually every structure is supported on soils, and those which are not either float or they fall over. So we're happy to try to build these foundations more sufficiently, and hopefully the roads last much longer. So I've got a couple of examples. I'll get through these within. I think we're pretty much on track to be. I'll wrap this up within 10 minutes or less. Have to take some questions. So
yeah, we're fine. We're fine, Jim.
Okay, thank you. So the first construction example is, again, there's going to be two of them here. Both are full depth, stabilized full depth reclamation. The first one we built in 2019, and you know, the soils out there were a mixture of sand, silt, and clay. Minnesota is largely glaciated, so this was a glacial terrain. The existing base material was approximately 4 inches, but it get difficult to even find in some places. And the existing asphalt ranged from 6 to as much as 15 inches. So, this is about a 10 or 12 mile piece of trunk highway. It had been there for many decades. And of course, there'd been, significant amount of overlaying happened. And so we had huge differences in the asphalt thickness. We went out there, we milled off 3 inches, set that aside so we could recycle that. And then we reclaimed everything else. So whether it was whatever was left, whether it was 3 inches left or 12 inches left, that all got ground up with the idea that we would mix back together the ground up asphalt and the underlying base materials, and then stabilize 6 inches and pave 4 inches of new asphalt. That actually the project everything looked great during construction. Actually won an award in the fall of that year for smoothness, but then big surprises in the winter. That following winter, huge amount of differential heave. So we got asked, that's how I sort of got involved. The materials office got asked, what can you maybe try to figure out what happened here, because it all seemed good during construction. So a couple of the sort of maps, and again, the way this looks in Minnesota, I guess on the right side, you can see here, this is an aerial shot, of course, and it's rural, sort of typical rural Minnesota terrain, farmsteads, some low areas, marshes, a few creeks, agricultural ground. As far as the mix design goes, we had cores all the way along this, not a huge number, but we had, I guess, around 40 spaced all up and down the project. That's how we knew we had that variation in asphalt thickness. And the idea was to blend the ground up materials into about 80% wrap, 20% aggregate base, mix in 1% cement and 2% asphalt binder, and build this new road. So that's of course somewhat of a challenge to get these mixes right, but that was the goal. And then we had to adjust some of these quantities on the way, depending on how this mixture actually worked out. But bottom line is everything was good during construction. Things looked great, no problems. We had 3 different rollers out there. The pad foot roller, then there was the pneumatic rubber tired roller, and then the double drum steel roller. So those 3 rollers were compacting the stabilized full depth reclamation. In order to look at all this information, we have this Veda software, and this is free now. I mean, we're still building it. You're welcome to join us. We're constantly improving the capabilities of this software, but right now it's available. You can either Google Veda, the name, or you can go to this Federal Highways website and then click on more information. You can download the current version, and this will allow you to import the contractor's data from the rollers, and then display all these different measurements, create these maps, and create all these asset records. So, we actually, the upper left is actually the measurement. The amplitude is measured. The upper right is pass count, so we know how many passes of every roller. The lower right is speed, roller forward, backwards at every point. And another example, lower left is this Trimble proprietary stiffness value. So different manufacturers have different stiffness values, but they're all essentially, the point is that we know we have a measurement, the actual amplitude of the drum, and we have location of the roller. So all this is good. And what I'm going to show in the next couple of figures only comes from the pad foot roller. So there's all these rollers, all these measurements, every foot of 12 miles, but you can crush through all that information using this software. And here's just a couple examples. This is a compaction curve for the map shown above. And so I carved, in this particular example, I carved this up so that these segments are only 25 feet long. You could be any length you want, but I carved up this 12 miles into 25-foot pieces, and then you can generate a compaction curve for every one of these pieces. This is just one of dozens of things you could do. But here's an example. This place, now unfortunately what happened here is we started compacting it and it goes down. That's not good, of course. The map shows red, and so this would be a questionable area. Now, of course, the roller operator is also seeing the map, and they're seeing that this area could be red. Now, unfortunately, if we don't fix this spot, here's the asphalt that was put on there many weeks later, and this is unfortunately not a good number. This index, this value of sort of 40, 45 on the, as you see on the left where that arrow is not typical. The rest of the job much higher. The rest of the job looks more like this, double that. So the asphalt typically has a stiffness like this. This is what we would expect. Unfortunately, we're not getting that. So that area is a place that should have been corrected. Now here is the base under that good asphalt. The value here of that stabilized full depth is around 35 or 40. That's, we got a compaction curve that looks reasonable. The other one clearly was not good. So we want to see something like this. Much of the project looked like this. That's why it performed relatively well, looked great during construction. Now, unfortunately, this is the roughness during the winter. It's a little bit busy, but I'll quickly just say that any value, everything, this is 10,000 feet, a couple of miles, anything above 100 on the inches per mile roughness is not good. And so we've got something terrible going on. What did we find out? We looked at these roller measurements. The map on the left is where there was vibratory compaction of the pad foot. The map on the right is where there was static compaction. Now, what happened was the operator, even though they were doing, they believed, everybody thought they were doing a great job. They were systematically, when they would reverse directions, they would turn the vibration off and then they would restart it. Well, what happened was they unknowingly created a huge amount of differential compaction, which didn't show up immediately. It showed up during the winter due to the apparent effects of the moisture. The water table is relatively high. We seem to have pumped water up into the grade and then froze it. When we looked, if you compare the measurements of roughness to the measurements of this differential compaction, we see a lot of problems. We see that there's some, not every spot, but there's this correlation between where we have high differential compaction, we have roughness. And so we learned from that experience, and we've made it clear to the contractors that they need to avoid this differential compaction, which everybody essentially understands, but they were happy to do better the next time.
John, we have 4 minutes.
Okay, very good. I'll just mention quickly, probably 2 minutes on this and then 2 minutes to wrapping up. So we'll be good. Thank you. The second project, again, this was just earlier this year where we built this one. And we had, of course, since we learned a substantial amount from that prior project, we were in contact with the contractors. They built this one, and they were all ears. They wanted to build a good road. And so this was similar, little bit different part of the state, but similar silt, clay, sand, kind of a mixture. Very similar kind of a project. And we then used intelligent compaction. Again, it's required for every stabilized full depth job in Minnesota. So the intelligent compaction was used. Here's an example that when we got started, the design did not call for reclaiming the shoulders. And so what happened was, this was just the first couple of days, we found that, and you might not be surprised by this, but because we had the main line was very deep, we had reclaimed it. a lot of material, and it turned out early in this, it was actually raining here earlier in the season. They had trouble compacting because the roller would bridge. It would ride partly on the shoulder. And if you look at this map here, you see that the blue is high stiffness values. The roller drum is sitting on the shoulder and it's not compacting the main lines. And so this was noticed both in the field. We had soft spots on the interface between the shoulder and the main line, and we had the records. They could see this. And so people got engaged. The contractor and the DOT personnel on this job said, we got to do something. They in fact decided to mill and reclaim the shoulders to create a much more uniform foundation. We solved this problem. And this was essentially, we're hoping that we measure the results of this project over the next few years and decades will be much better. So we were able to, again, mitigate this problem during construction. To wrap up, lessons learned are basically these tools, the dynamic cone penetrometer, lightweight deflectometer, intelligent compaction, are very effective asset construction tools. They help our contractors and our inspectors construct long-lasting, more resilient roadways. We continue this implementation so that the people's investments are well spent here. And we are just really happy to share any of these specifications with anyone on this call or in the future. The training videos we've got for this Veda software, again, we have to train all our inspectors. So we've got a huge amount of information, and we're just really happy to share any of that with anyone who's interested. So thanks again for listening.
Thank you, John. I have a question here from Alexander Mann that says, are you aware of seismic surface wave analysis in the use of strength testing of soils and compaction?
Well, somewhat, not as much as I'd like to be, but we actually have a current project that's looking more into using seismic surface seismic measurements, building and you can again contact me. We'll plug you into the project, but we have currently we're looking more at that. But yes, okay, that's another option.